So this session is future-proofing analytics ad hoc queries at petabyte scale. And I'm really excited to have you all here to share best practices about how to future-proof your analytics and allow you to innovate over time as data, technology, or challenges really change the way you derive insights from your data. My name is Tony Nguyen. I'm a principal consultant with AWS Professional Services. Been there 7 years actually now. My whole time here, I've actually been working very deeply with FINRA. And I'm joined here today with the representative for FINRA, Elan Bengui. He's the Director of Big Data and Performance Engineering at FINRA. And we're going to walk you today through working with and querying your data in AWS, how to choose the right tool for the job, and ultimately, how do you continuously improve ad hoc query for your users at petabyte scale? And we'll share an anecdote from how FINRA did it. This is a 300-level session, so while I will give a brief overview of the services that are included and involved, this session is really focused on how to evaluate your analytics and a deep dive into FINRA's 10-year journey. So what we're seeing these days is that data volumes are increasing at an exponential rate, exploding from terabytes to petabytes and sometimes even exabytes of data. Traditional on-premises data analytics approaches can't really handle these data volumes because they don't really scale well enough, and they can get really expensive. We hear from companies all the time that they're looking to extract more value from their data, whether it be through machine learning, deep analytics, things that really fit today's modern digital businesses. And it's coming from new sources, it's increasingly diverse, and needs to be securely accessed and analyzed by any number of analytics and people. And against this backdrop of really increasing data volumes and the desire to get data to your end users as quickly and efficiently as possible, we really have to think about how to prepare for this change in data volume and just the quality and type of data that we are thrown at. So let's talk about this sort of transformation from that traditional sort of data warehouse approach to what we're seeing today. Data typically, traditionally, has sort of accumulated in data silos, right? And it's really hard to do analytics on data when your data is in all sorts of disparate locations. This causes multiple problems, right? The data that you might need for a given workload might be split between multiple silos. It might not meet the price performance requirements that you have for your application. You might have different governance schemes on your different data repositories. And what customers are really ultimately looking for is a very highly scalable, highly available, secure, and flexible data store for all their analytics, right? That's a holy grail. You can do this with the data lake. You can store extremely large sets of data in a structured and unstructured manner using any sort of open data formats of your choosing, such as Parquet and Orc, and tag your data in a central searchable catalog. The crux of all this is that central layer that you see there, which is that data lake that's surrounded by all these sorts of analytics, whether it be relational databases, big data processing, or, say, machine learning. And we call this approach the modern data architecture in AWS, where you have scalable data lakes, you have purpose-built data services, services that are really custom-built, fit-for-purpose things for a particular application. Seamless data movement, the ability to move data between these services as well as to and from that central lake. A unified governance layer that allows you to really govern access controls across your data. And all this in a way that's really performant and cost-effective, right? Because that's what really matters to a lot of people. So here's the portfolio of what a lot of these purpose-built services that we have to offer look like. And a key to a proper data foundation is really choosing the best tool for the job. Letting developers, analysts, and architects use the best tool for the job and really enabling choice. And you should really break down your complex applications that are traditionally sort of monolithic, right? And break it up into smaller pieces, you know, the whole sort of microservices paradigm, and really choose what really makes sense for your application instead of settling for the lowest common denominator or something that really fits all cases, because then you're just kind of choosing mediocrity over purpose-built services. And that's what AWS services are really focused on, that sort of purpose-built mentality where it's optimized for your workloads. So for example, if you're a company like Lyft, and you have millions of geolocation and driver combinations, you don't want a relational database. It's too complex, it's too expensive, it's not really performant. You want something that's high throughput, high latency. That's something where DynamoDB really fits in. Or if you're a company like Peloton, and you're interested in microsecond latency for your queries, that's where something like Elasticache might fit into play. And my point here really is, again, choose the right tool for the job, right? The idea of a single database management system that can optimally handle any single workload is a thing of the past. That's not the world we live in today. We need to choose the right tool for the job, rather than settling for a monolithic compromise. And the world today is really focused on those purpose-built databases. And before I really get into really deep discussion about this, let's take a break from generalities, right? It's very common for people to think about, oh, this is a relational or a NoSQL database. I need to think about my schema freeness, or I need to think about how my data is very unstructured. It really boils down more importantly to the specifics of the data, right? You need to work backwards from your end requirements. And what is that? Typically, it's the purpose of the database and what your application needs are. And then you can break that down even further into data considerations. So the shape of the data, the size of the data, the compute characteristics of the things that you're going to be using to touch the data with. And so what does shape look like? Shape could be things like row stores, where you're looking at a record, a single record get, or a group of records, maybe perhaps a pull. Key value stores, where you're looking at really, really fast throughput and really fast ways of, say, ingesting the location of a particular IoT device. Graph stores, where you're looking at, say, recommendation engines, looking at the relationships between entities. Or a time series store, where you're looking at sort of telemetry or something like financial data. The size of data is also another important consideration. This is stuff like how much data do you actually anticipate to have, right? And you can think of it in terms of bounded and unbounded, right? Where bounded could be something like the number of employees a company will have, right? That's typically not something that's going to exponentially increase. Whereas the number of sensors used for an IoT application vary might well. Retrieval size is also very important. That single record get I was talking about, that's one kind of query. You also need to think about range gets, right? That this, let's say instead of one query, you want now 1,000 rows or 10,000 rows or 1,000,000 rows. What kind of query and tools should you be using for that? And the partitionability of the data is also really important. Does it make sense to partition the data? Car location data can be partitioned by zip code, for example, where payroll data isn't necessarily partitionable in any sort of meaningful way, right? You can think of it maybe on the order of like names, but at the end of the day, you have to add another sort of factor in there, such as the state that the person lives in. And then the compute. So things like the throughput of the tool that you're using, right? Or the latency. How fast can I get a query for where my car is today? How often does my data update? And how quickly can I ingest data into my data store? And all these sorts of data characteristics can be sort of summed up in a matrix that you see here. In this case, this is only a subset of all our services, right? But I think it encompasses a good range of how hot data, warm data, and cold data can express the characteristics of how that data store performs. So for example, Elasticache, very hot data. But in exchange for that, right, there's some trade-offs that you have to make for that speed. Durability is not as strong as something as, say, S3, right? If you're looking at Amazon EMR, you could use HDFS, but you could also use S3 and query data in place on S3 itself. So there's that sort of middle boundary between that layer of HDFS and S3 that you would consider in this case. So as a recap, let's talk about purpose-built data services. So you have Athena, which is our interactive query service. It makes it possible to query data in S3 using standard ANSI SQL. And it's fully managed. You don't have to manage any sort of infrastructure to make this happen. EMR is our managed Hadoop platform. It allows you to scale your clusters up and down seamlessly using all sorts of open source applications like Apache Spark, Flink, et cetera, to really perform analytics on your data. Amazon OpenSearch service, formerly known as Amazon Elasticsearch service, allows you to do that sort of document-based NoSQL quick pulls. Amazon Kinesis and MSK, MSK being our managed Kafka solution, allow you to do real-time analytics on your streaming data. And Redshift, Amazon Redshift, is focused on that data warehousing use case. Go ahead. So let's go ahead and dive a little deeper into those characteristics around data that I was talking about, right? Let's talk about Redshift first. So Redshift fits that data warehouse use case area where typically concurrency is not as high. You typically have a bunch of either analysts looking at it, but nothing too crazy. ETL is typically required for a data warehouse. You have some sort of ingest mechanism that allows you to flow data in. There might be some data transformations. Latency is typically on the order of seconds to minutes when you're doing a query, and sometimes they can go even longer, so on the hours frame, depending on how complex your query is. And what's really interesting about Spectrum here, for those who aren't familiar with Spectrum, Spectrum is a capability incorporated with Redshift that allows you to actually query S3 data in place. It allows you to actually have exploratory analytics be part of how you use a Redshift cluster. So in the case where, let's say you already are using your Redshift cluster for your data warehouse today, you can use Redshift Spectrum to join infrequently accessed data to your existing data, your hotter data inside of your data warehouse, and gain insights in that way. Let's talk about Athena. So Athena covers that ad hoc query use case. Concurrency in this case is also on the lower end. It's a soft quota. Somewhere around 25 concurrent queries at a time. But this is a soft quota, and you can get a limit increase for that. But at the same time, right, the typical use case for this is not high concurrency, right? You typically have some set of users that are doing some aggregation queries, some exploratory analytics on your data within S3. The important thing here to note is that in contrast to Redshift, which with the exception of Spectrum, uses native tables for hotter data that's stored locally on the nodes. Athena uses schema on read. That is, it reads data directly against S3 using information / metadata that's derived from the catalog to figure out how to query the data effectively and intelligently. It's always on, in contrast to Redshift, right? Redshift, you have to maintain and pay for a cluster that's on, whereas you can think of Athena as an always-on interface that you're not paying for unless you actually query data. It's primarily a query engine, but also has some ETL features as well. You can create a query and then create a table based off of that query, things like that. So what does an ad hoc analysis pattern with these two technologies look like? So in this example that you see here, you can see that there's this flow where you're querying data from multiple different data sources just to display analytics and visualizations with QuickSight. QuickSights are cloud native and serverless business intelligence service. So what crawlers are on the left are mechanisms that allow you to access your data store, extract metadata, and create table definitions within your Glue data catalog. These crawlers populate the central metadata catalog for this entire architecture. Once whatever data sets that you're interested in are cataloged and populated and defined as tables, we can then apply access controls to the tables. So Lake Formation is our integrated data lake service that makes it really easy for you to ingest, clean, catalog, and transform, and secure your data. In this architecture, fine-grained access control is enforced on the tables through Lake Formation. Once you have this all defined, you have it secured, you can then use Athena or Redshift to query those external tables in place without having to have an intermediate data store to query the data with. It's all in place. And there's a lot of advantages to this, right? Data freshness, the lack of need to ETL, all sorts of great things, lack of data duplication. And at the end of it all, authors of QuickSight can create a data set with Athena or with Redshift and display visualizations, dashboards, things of that nature. And it's important to note that not just QuickSight here, this architecture here is very flexible. You could, instead of using QuickSight, you could use Jupyter Notebooks, you could use SageMaker, or managed machine learning service. You could use any sort of JDBC or DBC tool that can connect to Athena or Redshift Spectrum to do these queries. A lot of power. It's also really important to note that the query functionality of Redshift and Athena isn't just limited to S3. Another part of data movement is really being able to query across data sources more than just your data lakes, right? So databases, data warehouses. There's a lot of cases where you aren't necessarily able to put your data inside of S3. And that's where federated data query within Redshift and Athena can really enable you to access data in a unified way. You can use familiar SQL constructs like joins, things like that, across multiple data sources for quick analysis without really having to set up and maintain complex ETL pipelines. So if your requirements at Athena or Redshift don't really quite meet, EMR is a great choice for a managed compute experience to run your queries. And it enables you to run solutions such as Spark and Presto, and you can choose to run your data natively against HDFS or separate your storage and compute where your data is in S3 and you can run queries against it. You can write your data back to S3, which really is the best practice in my opinion. When choosing a solution on top of EMR, it's important to note the various performance characteristics such as latency associated with Spark SQL or how Phoenix and HBase can really help you achieve low latency queries. While it's a managed service, you still have to put in some work to configure and tune your clusters. And you should also really consider the managed equivalents of the technologies here. So for example, if you're trying to run Spark SQL, you can use Glue as a managed service to do so. Or you can use Athena to run federated queries the same way that you would use Presto. Kinesis Data Analytics is our managed solution for easily transforming and analyzing streaming data in real time with Apache. It allows you to run standard SQL against your data within Kinesis, Kinesis PowerHouse, Kinesis Data Streams, or Amazon MSK. And it's basically a use case where you need to run SQL against streaming data. For the interactive use case, you can use tools such as Kinesis Data Analytics Studio to interactively query data sets using Zeppelin notebooks. In this example that you see here, we're taking a look at grouping IP addresses streamed from CloudTrail logs. You can also run SQL queries in Amazon OpenSearch. So OpenSearch service already supports over 40 SQL functions, data types, and commands to query your domains. And there is support for constructs such as joins, subqueries, persistent functions. And if you want, you can take advantage of OpenSearch's really high data freshness, concurrency, and latency. Typically, I see hundreds of thousands of reads per second for reads and millions of writes per second at the higher end of the spectrum. And although it really is focused on that use case of a NoSQL document-oriented database, OpenSearch might be a good fit for ad hoc traditional ANSI SQL queries if you have data that isn't really multi-nested and your queries fit within the SQL set that OpenSearch supports. Here you can see that the fetch size is also low, right? So typically you aren't going to be using OpenSearch to do a massive dump of your data. In contrast to perhaps maybe a more OLTP-oriented database where it's very common to do a select star and do a dump on a where clause, this is more of an ancient pattern for OpenSearch. Amazon Aurora and Amazon RDS also still have a place within all this. Relational databases should still be considered for your evaluation for your architectures. Aurora was originally designed to handle really high velocity data. Depending on the workload, with a single R5 16x large, you can exceed 600K select statements per second. Additionally, Aurora supports 128 terabytes within your database. So if your workload is OLTP oriented and you have a high need for concurrency and low latency, it's worth considering Aurora as an option. You need to make sure, though, that you're aligning the use case appropriately, right? Just because you can fit all your data within Aurora doesn't mean that you should use it for everything. So for example, for ad hoc query or exploratory analysis, those kinds of queries are typically more OLAP-based rather than OLTP. So something like Aurora, something more like Athena or Redshift is a better fit. So notice let's dive deeper into specific query patterns and map them to AWS services. So typically, these are the kinds of queries that you'll see when you're looking at a person's SQL Studio or what have you, whatever interface you're using. You can break down these queries into three distinct categories. Single record retrievals, range record retrievals, and OLAP aggregation. Breaking that down even further, when you're looking at queries that are typically done in a sort of exploratory analysis way, they are typically aggregate queries or a select star with a where clause, right? It's very uncommon to have anything that's more complicated than this, especially when you have someone that's just taking a look at the data, right? These are the kinds of queries that you're seeing especially when I'm looking at data. I'm typing in these kinds of queries to figure out and get a sense of what does the data look like, what does this grouping look like, things like that. And you can break down these user cases into different categories based on factors such as latency, scan size, fetch size. And it's really important to evaluate this based on OLTP and OLAP as well, where OLTP is more row-focused and OLAP is column-focused. And that's because most data sets consist of rows and columns, and most ad hoc queries don't use all the rows or all of the columns. You might have a couple hundred columns, but you really only care about a few. And this is very common for exploratory kind of stuff, right? And this use case aligns well with data that's in a columnar format. Think Parquet files, where you can skip reading the data that you don't really care about. So for example, if you have 100 gigabytes of data and you have a month of statistical reporting and you really only care about yesterday's data, you can cut out more than 90% of the data that you have in your query just by using columnar-based data stores. An additional consideration to look at here is concurrency, data freshness, and cost, right? So how many users can I use this data store at a given time? Do you issue queries at it concurrently? How fresh can my data be? What's the expectation of my users for how fresh this data is? And at the end of the day, how much is this going to cost me to achieve the things that I need to get done? So let's take a look at the single record retrieval, right? I'm going to break this, each one of those previous query cases that you saw before into what the best fit is for each of those. So for example, here, you're getting a single record. It makes sense to use Aurora or OpenSearch for less than 1 billion records. But when you have more than that, those kinds of data stores kind of have challenges getting at that scale. So that's where NoSQL stores such as DynamoDB or HBase really come into play. Range record retrievals look like this. So for ad hoc and exploratory analysis cases, these queries are really kind of uncommon. But sometimes it comes up, and so if you have that kind of use case, this is what you might be looking at. So again, for range record retrieval, when you're at the larger size, you might want to look at using something more NoSQL based for faster experience for your end users. OLAP aggregation queries typically look like this, where you have data that's typically grouped by some sort of column. At a smaller scale, OLTP databases can handle this kind of ad hoc query, but larger data sets at petabyte scale are more difficult to query without taking advantage of the performance characteristics of OLAP databases. In this case, you can use Aurora certainly for a data set that's 100 terabytes, right? It will fit. But you need to think about the characteristics of your query as well, right? If you're doing something like this very much column-focused query, it makes sense to use Athena or Redshift in this case. And in contrast to that last slide that showed OLAP aggregation, exploratory analysis cases typically demand really low latency for interactive use cases. And by really low, I mean something that's tolerable for a human, right? So seconds, minutes, I'm typically willing to wait 1 minute or 2 minutes. I'm not willing to wait 10 minutes or an hour, right? And so it's important to evaluate the runtimes of your queries against any solution that you're evaluating to ensure that your customers and your end users are happy. And it also needs to be considered in context of the query type and the data characteristics. So for example, Athena might actually outperform Aurora, even though I'm saying it's lower latency, just because it's perhaps a more OLAP-focused workload. And in terms of price performance, Athena would outperform it for aggregate queries. So let's go through some exercises really quickly to sort of discuss and get a sense of where people are for understanding what I just went through. So let's talk about exercise 1. So here's a scenario where you have a data set size of 100 terabytes. You want to serve multiple internal Tableau dashboards, and you're typically using OLAP aggregation queries inside of it. Multiple joins, very large tables, and a few tables are actually very large, but you don't really access them that much. You have a concurrency factor of 30 concurrent sessions, / queries, your scan size on the terabytes level, your fetch size is low, your data freshness is 1 hour, and your query latency is in minutes. Which solution is best for here? Does anyone have, raise a hand, yell it out? You can use Athena, but is it really the best fit? If you want something that's performant and you're serving multiple Tableau dashboards. Any other suggestions? It's really only 1 or 2 choices. The Redshift, in this case. The key is you have a few tables that are infrequently accessed, implying that you actually have a bunch of tables that are very frequently accessed. Right? So you would store those hot tables inside of Redshift, and then when you needed to, you would use Redshift Spectrum to query the infrequently accessed data that's inside of S3. Let's go to another one. So you have a data set size of 100 terabytes a month, and what it's doing is it's serving an external data API where 100 partners can download their data at the end of each month. Concurrency is 100, your scan size is on the terabytes, your fetch size is really high. Your data freshness is 1 month, right? People don't really care about how fresh the data is. And the query latency is 6 hours. That's the SLA for this. So what's the right tool for the job here? Anyone? The answer here is Spark SQL and EMR. It doesn't necessarily have to be Spark SQL, but in terms of the underlying platform, EMR makes the best sense here, because it's something that isn't necessarily interactive. Your users can stand and wait. What this really is a transformation job. And even though it's using a SQL query for the job, someone can issue the query and walk away and wait for the EMR job to finish processing it. Alternatively, you can use Blue to actually manage that experience for you. Okay, another one. Data size 100 terabytes. You have 10,000 customers. Each customer has about 10 users. Each customer queries their own data and performs OLAP aggregations on their data. Fetch size is low, scan size is on a gigabyte, data freshness is 15 minutes, and the latency demanded is 1 minute. Any ideas here? The answer here is Aurora, close. And the key here is that even though I'm saying that OLAP aggregations make sense here, that sort of multi-tenancy and the concurrency requirements rule out the ability for Redshift or Athena to fill the job. Similarly, right, the query latency requirements also make it difficult for, say, Athena to fit the bill here, depending on how the data is structured. Because when you have a multi-tenant environment, you can't really assume that everyone is structuring the data the same way. This would actually be a very costly deployment, but that's what the requirement is. Last exercise, data size 5 petabytes, ad hoc query for interactive data discovery. And there's a desire for serverless, really by management here, to minimize cost, and they don't want to deal with managing any sort of hardware anymore. Concurrency, not that much, 10 concurrently. Scan size is on megabytes scale, fetch size is low, and the query latency is on seconds. Any suggestions here? This one's Athena, that's right. Because I hope this makes everything a bit more clear as to how, at least internally, I go through how to choose the right tool for the job duties. And so the key takeaways that I really want you all to take out of this is to work backwards from those requirements, just like I did, and ask the right questions around the data characteristics. Had I had more time, I'd go through the entire process of how I sort of do data discovery, how I figure out the query characteristics, how I figure out how to derive the expected SLAs from queries. But in the absence of that, all I ask is that you ask the right questions, and you figure out what your end users expect from your queries, and what the business actually needs. And those could be a couple of factors, right? What are their end customers? How much money / budget do they have? What are their security concerns? And ultimately, you want to choose the right tool or tools, right? You can combine tools together for the job and decouple compute from storage where possible, because you can really save a lot of money by doing so. And ultimately, you want to use managed services and serverless compute so you can stop doing undifferentiated heavy lifting and focus on your own unique challenges. So with that, I'm going to go ahead and pass it over to Alon to talk about FINRA's particular journey on all of this.
Thank you, Tony. A lot of useful information, and that was great, Tony. Thank you for having me, and thank you all for taking the time to be with us today. I'm Andy, and I oversee the performance engineering team at FINRA. I've been working at FINRA for the past 20 years, and I've been involved in many technology transformation and innovative projects.
Towards.
There you go. So, how will we spend our day today? So, in terms of agenda, first, I will give you an overview of FINRA. Who is FINRA? And what is FINRA mission? Then, I will give you a quick overview of our existing big data and analytics platform. And then we will go to a concrete sample. We will review the life of a FINRA analytics application over a 10-year period and how we change it from running on data appliances on-prem to a serverless technology. As you will see, we are constantly looking to improve our application in terms of cost, performance, and ease of use. So, who is FINRA? Our mission is to protect investors and to regulate security market, looking for market manipulation, fraud, as well as insider trading. Our company collects data from firms and exchanges, and basically what we are doing is protecting you, making sure that no fraudulent activity is going on the stock market. The nature of our business makes us a big data company. For example, we are performing 500 billion checks every day. We are operating over 150 petabytes of data in the cloud. And it takes a massive undertaking to manage and process that data. It's over there. Oh, okay, I put it now. Sorry. So the growth over the past couple of years has skyrocketed. This is due to the CAT project that we have been operating since 2019. The CAT initiative is a reporting utility commissioned by the SEC to enable regulators to fully track trading activity and boost transparency. And since then, the volume keeps growing. We had multiple days in 2021 where we had to process over 400 billion transactions for a single day. So this is a high-level overview of our platform in the AWS cloud. But for today, let's focus on the analytics part. We have the possibility to reconstruct the market activity at any given time by doing the following. First, in batch mode, we run detection models who look for market anomalies and generate alerts if it finds some. Then those alerts are sent to our investigator. They can interactively query the system to get a better understanding of it. We are running our analytics platform using a plethora of tools and services, such as Apache Spark, Apache Hive, Amazon Redshift, Amazon Presto, Apache HBase, Amazon Athena, and many more. So let's deep dive on our lifecycle viewer application. And let's review our 10-year journey. Over a 10-year span, we have changed the application underlying infrastructure and technology 4 times. We went from running data appliances on-prem to the EMR HBase solution. Then we migrated the application to an EMR HBase on S3 solution, which is full open source. And finally, in 2020, we moved it to Amazon Athena. Through this presentation, I'm going to use a common thread, the triple constraint, a bit like in project management analogy. But in our case, quality of the solution will be based on 3 criteria: performance, cost, and ease of operation. And for each solution, we will calculate a scorecard. But first, I think it's important that I provide you the application requirement. The application needs to ingest billions of records on a daily basis. The retention period is 6 years. Therefore, our overall data set size will be in trillions of records. user, and we have 1,500 of them, needs to be able to quickly retrieve stock market information based on a life cycle ID or a set of key fields. The application needs to sustain load during peak up to 100 queries. That 90% of the query, because they retrieve a large amount of data, needs to finish under a minute. And of course, from a security perspective, everything needs to be encrypted, at rest, and in transit. So, before the cloud, 10 years ago, we can call it a silo architecture. We were running our IT in our own data center with a bunch of different platforms. Data appliances, storage devices, multiple databases, tapes, etc., and etc. Our data were spread all over the place. We were facing multiple challenges because we were constrained by storage and by compute capacity. We had capacity to store only 2 years of data on it. We had to deal with competing workloads as ETL and analytics query were running on the same platform. Yes, the solution will be add more nodes, but adding more data appliances is first very expensive, and secondly, it takes a long time. It could take us up to 3 to 6 months to add those appliances into the infrastructure. Another big challenge was, where is my data? They were spread across multiple platforms. And it was difficult to locate them and to find them and to access them. On top of that, business users could request to access data that were more than 2 years old. Technology had to look for them. And they were most of the time back in the tapes. So we had a dedicated team just for tape management, backup, and restoration procedure. All the criteria are in red in that scorecard. Nobody is satisfied from a business and from a technology perspective. From a performance, it was very poor. For instance, one job could take all the resource cluster and all the other workloads were queued. For that specific, we had a dedicated team monitoring the system usage and were in charge of killing workload if they were taking too much CPU or too much memory. The cost of the solution was very expensive, cost of the appliances, cost of the storage, cost of the license, etc., and etc. And it wasn't easy to operate. Hardware maintenance and software upgrade had to be done during the weekend. It was taking months to add new capacity. I can tell you life was very hectic at FINRA back in those days. All right. So sorry, I cannot get you to this. So in 2000, we are in 2013, and a strategic decision was made by our CIO. If we want to fulfill our mission and to protect investors, we need to move to the public cloud as soon as possible. Public cloud is elastic, and you have unlimited capacity from a storage and compute perspective. So the lifecycle viewer is one of the first applications moving to the cloud. We design a solution using Amazon EMR and Apache HBase. We provision and operated a large and long-running cluster using a lot of storage-optimized instance type. Therefore, we had a lot of disk space available and a lot of CPU. We kept loading data on a daily basis, and we took snapshots for backup purposes. And we store our snapshot into S3. And the idea was that if we lose the cluster, we will restore the system from the snapshot. But a few years later, we reached the point that the snapshot has grown so much that we could not, in timely manner, restore the cluster from backup, and we will be missing our RTO, our recovery time objective. So from our scorecard perspective, from a performance perspective, the user queries were performing at speed of light. Milliseconds retrieval time. I remember the standing ovation by the business user compared to the previous solution. From a cost perspective, it's way better than the previous solution, but still, it's expensive, as we are using the largest EC2 instance type available at that time. We are also running HBase, using a third-party commercial license. The license cost was expensive, and we're adding up as we had multiple environments, QC, stress test, and production. From an ease operation, definitely it's better. We don't need to deal with steps anymore. We have everything online under the same storage device. So it's very easy to retrieve the data. And it's much easier to add capacity. As we are using EMR, it takes just a couple of minutes to add more nodes to the system. But because of the backup restoration issue, we were starting to freak out if we are losing the cluster. It will take way more time in order to restore the service. So we are making another architecture decision. We said we need to move to a data lake architecture, meaning that now our data will be stored on Amazon S3. And our system will have access to any historical data at any given time. For this, we need a robust data catalog. AWS Glue and Lake Formation were not yet available at that time. So we had to develop our own data catalog solution. From it, we can retrieve any market data via simple API call, taking care of access control, and it's built in with the right security mechanism. With this new data lake architecture concept, we have achieved separation of storage from compute. And it makes all our system much easier to operate. Now that we store all our data in S3, protecting our data is key. At the end, it's very simple. We encrypt everything. We encrypt data at rest, we encrypt data in transit. And we also know that in Amazon S3, our data are very well protected. I'm not going to describe all the benefits of S3, but in our case, we are using versioning. We will never lose any data. We are using cross-region replication. which automatically copy data from one region to another region for disaster recovery purpose. And we are using Glacier for data archiving, long-term backup, and for cost saving. Now that we have this data-led architecture, we can revisit our lifecycle viewer application. And we decide to move to an HBase on S3 solution. From an architecture standpoint, this solution looks very much like the one before. It's based on EMR and HBase. But the main difference between the two solutions is that we switch to the HBase open source. Our data are stored on S3, not on HDFS anymore. Looks like small changes, but it makes a big difference, as it gives us a lot of flexibility. Be able to use less expensive hardware instance type, because we are no longer storage bound. Be able to mix reserve and spot instance type. We have the ability to scale down the cluster at night or during the weekend. The ability to start the cluster in any AZ. And reduce the cluster starting time in less than 30 minutes. So, from a performance perspective, yes, response time are not in milliseconds anymore, but they are good enough for the type of query that we are running. Cost, it's a big win. 75% cost saving compared to the previous solution. First, it's a full open source solution. We can use smaller instance types that are widely available on the spot market. We can shut down clusters in a lower environment and restart them when we need them. From an ease of operation perspective, it's much easier than before. We can easily scale up, scale down the cluster. We have no compute or storage constraint. So the solution is almost perfect, but it still requires a lot of maintenance. For instance, we are using Kerberos for internal encryption. Resources that are not always easy to find on the market, a lot of engineering work, a lot of operation work needs to be done, making sure that the backups are run, so we monitor the system constantly, making sure that we are not losing node, we need to replace. So a lot of operation going on with that solution. So we've been looking at serverless computing for a while. What we like in serverless computing is to be free, to free us up from infrastructure management. We strongly believe that our focus should be on building application instead of configuring it. And we gave a try at Amazon Athena. So, one of the main requirements for us to adopt Athena was the Hive external metastore integration. As I said earlier, we are not using AWS Glue or lake formation. Here is our data catalog, and it's the place where we store all the table definition and schema. The announcement of the Hive external store integration was a game changer for us. It was a major green light for us to adopt Athena in our architecture. Another concern that we had with Athena was about performance under heavy load. Remember, I told you we could have up to 100 concurrent queries running at the same time. So we gave it a go, and we put Athena under stress. We loaded 1 year of data, which represents 25 trillion of records, or 2 petabytes of data. As you can see on the white graph, we ran a 1 hour stress test with a sustained load of 100 concurrent requests per minute. On the orange graph, on the first line, you can see that we did submit more than 15,000 queries, and we observed 17 failures only. It's a success ratio of 99.9%, proving that Athena is reliable under load. In terms of query response time, the results were also very good. The average response time was 17 seconds. The 95th percentile response time is 32 seconds, which is well under our 60 seconds requirement for that specific application. From a scorecard perspective, it's all green. Performance, it performs very well, even under load, as I just mentioned in the previous slide. And as the query response time are within the application SLA. The system is highly available, it scales up, scales down automatically. We don't have to do anything. From a price perspective, we only pay for what we use. It's a pay-per-query model, and you only pay for the data that you scan, which can lead to significant savings. And from the ease of use, well, it's serverless, zero infrastructure, zero administration. AWS manage everything for you. For instance, instance capacity provisioning, patching activities are handled by AWS. You can really switch your focus on building the application instead of maintaining or operating your application. Getting good performance with Athena requires a lot of work. It's not easy as it sounds. Remember, the underlying storage layer is Amazon S3. Therefore, query performance is strongly dependent on how you organize your data on S3. So we follow 4 principal design. We design our schema using data partition and data bucketing techniques that align with our common query filter. We use Apache ORC format with a large stripe size. Large stripe size enable efficient read on S3. We also look at our file size, as it matters a lot with S3. The sweet spot for us is 256 meg to 1 gig in terms of file size. And we collaborate, we work with the AWS S3 teams in order to pre-partition the prefixes. I don't really know what they are doing behind the scenes, but every time we ask them to pre-partition a bucket or a prefix, we can see some performance improvement. So, in terms of takeaway, I think there is many of them, and I've been listing them in this slide. But the main one, from my perspective, is keep seeking for delivery of new services, new hardware, or new software. Take advantage of new hardware that are faster or cost effective, or are very cost effective. don't forget to upgrade your software stack. For example, we've seen a 20 to 25% performance improvement by upgrading from Spark 2 to Spark 3. And keep trying to improve your process, your application, your code. Keep looking. I'm sure there is some way to optimize anything in your stack. And by doing so, you might be able to significantly reduce your cost, increase your performance, improve your security, and reduce the burden on your operation team. Thank you for listening.
We have 2 minutes left for any questions. Anyone might have? Happy to field them or for any questions for Alon as well. No questions? Great, thank you.